Hey there, and welcome to this video. Today I will implement the siren. It was introduced in the paper Implicit Neural Representations with Periodic Activation Functions. As you probably realized, I'm on the official GitHub repository. The official code is more general and among other things, it can be used to represent audio and video. Anyway, all the credit goes to the authors of this paper and the code. Alright, let me give you a quick description of what the setup is. You're probably familiar with the task of image classification. There we have a data set of images where each image has a certain label assigned to it. So in this case, it's a classification dataset and each sample represents one image. Let us now completely abandon this paradigm and assume we only have a single image. For example, it's going to be a grayscale image with both height and width equal to 20. We can actually think of the image as a function that maps the pixel coordinates to the intensities. So in other words, if we have an image, we can create a regression dataset out of it. There are two features, which are the two coordinates, and the target is the intensity. And nothing prevents us from using a neural network that approximates this mapping. And this is where the Siren neural network comes in, because it works extremely well for this task. Anyway, you're probably thinking, that's cool, it can represent an image, but what else can I use it for? First of all, as mentioned before, we can also use sirens to represent video and audio signals. Additionally, there are other really cool applications, for example, solving partial differential equations, image editing, and image inpainting. Anyway, this video is going to be focused on creating the representation, and we are not necessarily going to talk too much about the applications. All right, let us now start with the implementation. Before we start implementing the Siren architecture, let us now implement a specific way of initializing a linear layer. Alright, so this layer will take the weight of the linear layer and it's going to modify it in place. The initialization will depend on whether this is the first layer of the architecture or if it's not. And lastly, we will have a hyperparameter omega that will be used for scaling. Given the weight matrix, we extract the input features. As you can see, we will always initialize the weight with a uniform distribution, and the bound will depend on whether we are in the first layer or a later one. So the authors of the paper propose this initialization strategy because it will lead to the activations of the neural network having some really nice properties. Now we're ready to implement a single layer of the Siren network. Right, the input features, output features, and bias are going to be used to construct a linear layer. IsFirst and omega are two hyperparameters. Isfirst will determine whether we are in the first layer of the neural network, and omega will be used for scaling. And finally, we will give the user an option of passing a custom initialization function. And if they don't, we will just default to the paper initialization function we defined above. We instantiate the linear layer. We initialize the weight matrix of the linear layer. The reason why we allow for a custom initialization function is that we want to inspect how the activations of the neural network behave under different initialization schemes. However, for training, we will always use the paper initialization that we defined above. When it comes to shapes, the forward method behaves exactly like the linear layer. Note that I call the first dimension number of samples, however, in our case, I can just name it the number of pixels. Anyway. The forward pass itself is extremely simple. We take the input, we run it through the linear layer, then we multiply with omega, and finally we use the sign activation. Alright, let us now move to the actual neural network. So the Siren neural network is nothing else than a bunch of sine layers followed by a linear layer at the very end. Here we make a simplifying assumption that all of the hidden layers are going to have the same number of features. We will have two different omegas, one for the first layer and then another one for all the hidden ones. As before, we will allow the user to specify a custom initialization scheme. Internally, we will be using the sequential wrapper. So we will have two input features representing the coordinates of a given pixel, and we will have a single output which will represent the predicted intensity. So we instantiate an empty list and then we append the first sine layer to it. We iteratively define all the hidden layers and all of them will have the same number of features. We instantiate the last linear layer and we initialize it accordingly. Finally, we create the sequential module. So the input is going to consist of multiple pixel coordinates, and the output is going to be the predicted intensity for each of the coordinates. The forward pass is extremely simple because we just use the sequential module. Anyway, we have implemented the network, and as you would probably agree, it was extremely simple. The Siren is nothing else than a multi-layer perceptron that is using the sine function as the activation. Anyway, before we jump into training, let me show you how the activations of the Siren look like. Alright, so I set the seed in order to have reproducible experiments. And now the idea is to define a couple of different initialization functions and then inspect what influence they have on the activations of the Siren network. So once initializes everything with once, I is an identity matrix. Default should be what Torch is doing by default, if I'm not mistaken, and that is the Keiming uniform. And finally, we will provide none, which, as we know, means that we will use the initialization proposed in the paper. For each of the initialization schemes, we will have a separate logging folder and a separate summary writer. Here I create a forward hook that will take the activations of a given layer and log them with TensorBoard. I instantiate the Siren and I make sure that I pass the correct initialization function. And here I iterate through all the submodules and I make sure I register the above forward hook. Here I prepare an input that is going to be uniformly distributed in the interval -1, 1 for both of the coordinates. This is exactly the kind of input we will be dealing with while training because we will scale the coordinate grid into the interval -1, 1. And I run the forward pass, and since we registered the forward hooks with multiple layers, they're actually going to be executed. Alright, so the script was run, and now we just want to open TensorBoard. We are in the histogram section, and as you can see, all the layers are conveniently numbered based on their order. When it comes to the input, it is clearly a uniform distribution in the interval -1, 1, irrespective of the initialization scheme. Let us now focus on the rightmost column because it represents the paper initialization. It seems like after the linear layers, the distribution of activations is always normal. And after sign layers, it seems to have this funny shape, which is actually the arcsign distribution. And again, it seems to be consistent throughout the network. If you look at the ones, it seems like from certain point onwards, we are not having any normal distributions, and it's always this arcsign-like distribution. However, the range is different for linear and sign. When we look at the identity initialization, there doesn't seem to be a clear distribution pattern. And finally, the default one actually seems to behave similarly to what the paper initialization is doing. Anyway, I just wanted to show you a couple of different initialization schemes and prove that the activations are really dependent on them. In the paper, the authors actually proved that under certain assumptions, the activations will be always switching between the normal and the arcsign distribution. One of the main implications of this is that one can create arbitrarily deep siren networks. Additionally, this initialization scheme seems to be the key ingredient to make the training work really well. Alright, so we are back in the main script and we would like to implement the training functionality. To do that, we will start with a function that generates a grid of coordinates. Alright, so we will make an assumption that our image is a square, and the only thing we pass into this function is the side length. And then it will generate a grid of coordinates inside of this image, and it will return it. Alright, so we use NumPy's mesh grids to generate rows and columns, and at this point they are still in 2D shapes. And then we just flatten both of them and stack them into the final array. So the first column of this array will represent the row coordinates, and the second one will represent the column coordinates. Alright, and now the goal is to write a dataset that is going to yield the coordinates, the intensities, and the gradients. At construction time, we will give this dataset a grayscale image. And internally, it is going to define multiple attributes. The first one is the size, representing both the height and the width of the image. Then a grid of coordinates. This attribute will hold the approximate gradient of the image in both directions. Here will be just the norm of it. And finally, the Laplace attribute will be holding the approximate Laplace operator for that given image. Here we just check whether the image is grayscale and the width and the height are identical. Here we use the function that we defined above to generate a grid of coordinates. So we take the original image and we apply the Sobel filter in both of the directions. The Sobel filter actually approximates the first order derivative and additionally adds some smoothing. So if you're wondering why I talk about gradients, I guess now it's the perfect time to talk about another really cool feature of the siren. The siren has a very nice property that if you take the derivative with respect to the input of any order, you will again end up with a siren. That means that the higher order derivatives are not going to be zero, and therefore the siren is very well suited to represent natural signals. We can actually use this property and supervise our network on derivatives of any order rather than just the zeroth order intensities. And that is exactly the idea behind what we are doing here. So we take the gradient and we compute the norm over both of the directions, and this way we again have something that has exactly the same shape as our original image. And finally we also use the Laplace filter to approximate the Laplace operator. Note that both the Sobel and the Laplace functions are implemented in SciPy. Here we define what the size of our dataset is, and it's nothing else than the number of pixels. Note that this is slightly different to the official implementation, because there they would set the length equal to 1, and they would always yield all the pixels of the given image. Alright, and now we want to implement the get item. We will give it the index of the pixel, and then we will just return all the interesting things that we know about this pixel. We extract its absolute coordinates. We unpack it into the row coordinate and the column coordinate. Here we take the absolute coordinates and we turn them into relative ones that are going to be in the range -1, 1. These relative coordinates are actually going to be the two input features to our neural network. In general, in machine learning, it's a good thing to scale your features. And additionally, as we saw a few moments ago, if our features are uniformly distributed in the range -1, 1, then the activations throughout the network are going to be really nice. So as you can see, we create a dictionary where each entry represents some information about the coordinates of that pixel. So for example, the relative coordinates, the absolute coordinates, the intensity, the gradient, the Laplace, and so on. And what's really important is that the relative coordinates will be used as features. When it comes to the intensity, gradient, and Laplace, they can all be used to supervise the network. Note that this is extremely powerful because not only can we supervise on the intensity, but we can also supervise on any higher order derivative. So as you've just seen, the get item was returned in a dictionary. And the question is, how is the data loader actually going to process this dictionary? All right, let us now write a minimal data set. So the length of this data set is going to be 8, and the get item will return a dictionary. And what we're trying to answer here is how exactly does the data loader create a batch? We instantiate our data set, and we instantiate a data loader with batch size 3. As you see, the default behavior kind of depends on the type of the value of the dictionary. A was originally an integer or a float, and as you can see, the data loader batched it into a one-dimensional tensor. B was initially a list of 2 elements, and here the data loader actually did the batching element by element. The C and D are both torch tensors, and they are identical. What's really important is that this default behavior turns NumPy arrays or floats into torch tensors. Alright, so now we understand what is going to happen when our get item returns a dictionary. But what if I was not happy about this default behavior? Well, there is a solution. Here I'm looking at the docstring of the data loader. And here we see there is this collate function, which is a callable, and we could actually use it to define any batching strategy whatsoever. I'm not going to show you an example, but just be aware of it. All right, so we're back in the implementation. And now the only thing left is to write some gradient related utilities that will be using Torch's autograd. Before we start though, let me just give you a quick overview on higher order derivatives in Torch. So I just copy-pasted a loss function that is nothing else than a single variable polynomial and all of its derivatives. And we'll try to do this calculation in Torch. Actually, it's extremely simple, and there's just one small trick that you need to be aware of. So first of all, we need to directly use the Torch autograd, which is a little bit more low level. And it correctly computed the derivative. And now to get the second order derivative, we would want to do something like this. However, as you can see, it doesn't work. And the reason why this is not working is that the dx loss does not have the requires grad set equal to true. And the trick to guarantee that the result of this differentiation can again be used as an input is to use the keyword parameter create graphs and set it equal to true. Alright, so as you can see, now it is the case. And if we do this procedure multiple times, we can get derivatives of any order we want. Alright, so we're back. So we've seen that we can approximate derivatives and higher order derivatives by sliding a filter along the image. However, we also want to have the predictions of these. In other words, we want to compute the gradient with respect to the input of our siren, as well as higher order derivatives. Alright, so our first utility function will be the gradient, and it will be doing more or less what you've just seen in the small tutorial. However, we'll be applying it to the function of more variables. Alright, so we take the gradient of the target with respect to the coordinates. Alright, the next one is going to be the divergence. Alright, so what is different here is that the input is already a gradient, and here we want to compute the second order partial derivatives and only sum up those that are not mixed. So let me just maybe add a node here. And now we just put everything together to get the Laplace operator. Alright, so first of all, we take the gradient with respect to the coordinates, and then we are going to differentiate the gradient one more time and sum up the non-mixed partial derivatives. Alright, and now we can finally write a training script. Alright, let us start with image loading. We load a PNG image, and the intensities are going to be in the range of 0 and 1, and we rescale them to be in the interval -1, 1. Also here I define a downsampling factor, however you don't have to have it, and its main goal is to make the training faster. Alright, let us now instantiate our pixel dataset. When it comes to the batch size, I set it equal to all pixels in the image. However, you can also set it to a lower number. Note that the authors actually propose to use the entire image at once. I noticed that for the training it really helps. So yeah, the idea here is that we are going to try two different networks. First of them is going to be the Siren, and then we will have a vanilla multilayer perceptron with ReLU activations. Here I let the user decide what kind of target we want to supervise on. Note that we can also use all of them at the same time or combine them in any fashion. Alright, so here if the user selected Siren, then we just instantiate our Siren. If the user selected a multilayer perceptron, we build it from scratch. Also here I'm initializing the weights with the Xavier normal initialization. I think I've seen it in the GitHub repo, I might be wrong. We instantiate the data loader. And here I will just write a very simple training loop. Note that we're not splitting the dataset into validation, test, and training. In a way, our goal is just to overfit the training image. Alright, so we have our batch and we're going to extract the features out of it, and they are nothing else than the coordinates. We make sure that we set the requires grad equal to true, because this way we'll be able to take the derivatives with respect to the coordinates. We extract the target, which is the intensity, and in a way it's like the zeroth order derivative, it's just the function itself. As discussed, the data loader is going to collate the intensities into one-dimensional tensors. And we actually want to add the second dimension so that we can comfortably compute the loss. Alright, so we run the forward pass and we get the predicted intensities. So if the user wanted to use the intensities as the targets, we just compute the mean squared error between the predicted intensities and the ground truth intensities. If the user specified the target to be grad, then we use our gradient utils to compute the predictions. And as the ground truth, we use the image after applying the Sobel filter to it, which is an approximation of the gradient. The loss is again the mean squared error. And finally, if the user selected the target to be Laplace, we will be supervising on the second order derivatives. At the end, we just add the torch boilerplate, which is computing the gradients and taking the optimization step. And what comes next is just some minimal logging functionality that will help us visualize what's going on during the training. Here we just prepare the prediction images, and we will iteratively set all the pixels to the right values. Here, for each batch, we extract the coordinates, we run the forward pass, and then we also compute the predicted gradient norm and the predicted Laplace operator. And then we just take these per coordinate predictions and use them to populate the corresponding pixels in our images. Note that if batch size is equal to the number of pixels, there will be only one iteration and we will populate all the pixels at once. And here we just always plot the ground truth and the prediction for the zeroth order derivatives, which are the intensities, the first order derivatives, and the second order derivatives. All right, then we're done. I think I will just run this with a couple of different hyperparameters and different settings, and then I will just explain the results. Here I actually computed the norm twice, so that's not correct. All right, I'm going to show you a series of different results. The ground truth will always be in the left column and the predictions will be in the right column. The first row represents the intensity image, which is just the actual image. The second row represents the gradient norm, and finally, the last row represents the Laplace operator. Note that I did not really look for optimal hyperparameters. I just took the training script and ran it for a couple of iterations, so please take that into account. So let us start with the Siren network. We see that if we supervise on intensities, we can get an almost perfect representation of the image in a couple of iterations. And it seems like both the first and the second order derivatives are matched really nicely as well. Similarly, if we supervise on the gradient, the results look really impressive. Note that under this setup, one could add an arbitrary constant to our Siren and the gradient would stay the same. Luckily, Matplotlib actually scales the image intensities before plotting them, so we don't have to worry about anything. Here you can see the results when using the multilayer perceptron with the ReLU activations. I guess the major difference compared to the Siren is that the Laplace operator of the prediction is just black. This is because the second order derivatives are equal to 0. When it comes to the predictions, we can see that they are not necessarily smooth. Anyway, I guess by having more trainable parameters, one could squeeze out better performance out of this architecture. However, the Siren is clearly doing better at capturing natural signals, and I think that is the main takeaway. Anyway, that's it for today's video. I hope you enjoyed it. It was slightly tricky to decide on the scope because sirens are very versatile. If anything, I hope I managed to spark your interest, and I would more than encourage you to check out the paper and the official repository. Most importantly, all credit goes to the authors. I just hope I did not make too many mistakes. Anyway, thank you for making it to the very end. Let me know whether you liked the video, and if you have any ideas or feedback, I more than encourage you to leave a comment below. See you next time.